Yeah, hello everyone. So I'm going to present our editor that can efficiently edit up to around 100 million splats. And we also wanted to make sure that it works in virtual reality, where we can achieve about 90 frames per second for up to around 10 million splats. So, so this is what it looks like. Here we have it in virtual reality. We have a couple of features that we can use here, like first delete this table here. Then we have an asset library where we already have some pre-cleaned assets we inserted in here, which we can then insert into the scene. Yeah. Another thing you can do is you can, of course, select stuff and then duplicate it. And here we first get rid of this garden scene, of the table here, and then use this selection and duplication in order to fill the hole with the patches around here. And it turns out that Gaussian splats are really nice for this kind of hole filling, since they're kind of a little bit volumetric, fussy, and if you leave a little bit of overlap, it blends together very nicely in a seamless fashion. So yeah, with a little bit of work here, we end up with a filled hole and a nice lawn in this garden where the table used to be. And yeah, another thing, of course, in virtual reality, select some splats, and then you can move them around, place them somewhere else. Yeah, and then you can also do some painting for some important use cases, like paint some graffiti on the walls of abandoned buildings or ruins. Or let's assume this is some kind of statue, an old Roman or Greek statue. And these used to be colored, and with Splatshop we can recolorize them. So the most important feature of all is probably undo and redo. So we took a look at a little bit here on, well, how can we do this efficiently, how much performance does it take, how much memory. And yeah, the easy thing is for selection, for example. If we select something and we want to undo it, we just need a splat mask, a bit mask of 1 bit per splat. That indicates whether the splat has changed or not, and that's how we can undo and redo that. For painting, we need a little bit more memory, so 12 byte per splat for the index of the splat that has changed, and the original color value. For transformation, we would need a lot more memory because we've got positions, rotation, scale, and most important of all, the spherical harmonics. So if you rotate something, we need to update the spherical harmonics. And transforming all of that and keeping the original values would require too much memory. So for now, here we settled with simply storing the transformation matrix and then applying the inverse. So this part here is currently lossy, but for the most part, it works fine. So let's take a little closer look at undoing and the performance of undoing stuff. When we paint something, and we start a paint stroke by pressing the left mouse button or the trigger button on your controller, we first duplicate the color buffer. Then we do the painting, and at the end of the stroke, when we release the mouse button, we then compare the original value and the changed value. And from that, we create a compact diff that only contains the index of the modified splats and the original color values, and that's how we can store this information with relatively few memory if we just paint a small part out of the entire scene. Performance-wise, it looks like this here. So let's take a look at the bottom one, the campus scene with 28 million splats. Here, painting with a brush that covers the entire scene adds about 1.7 millisecond to the frame duration on an RTX 4090. So yeah, that's okay. For compaction, which happens at the end of the brush stroke, we need up to around 9 milliseconds. And that's because we need to do a little bit more stuff here. So first of all, we need to count how many splats have changed in order to allocate as much new memory as we need. So yeah, count it, one kernel counts how many changed, then we do a new CUDA mem alloc, and then we have another kernel that populates this stuff. So this can be up to 9 milliseconds, but it's still okay for just releasing your mouse button. And then the undo and redo itself is already it's also quite fast, just about 2 milliseconds if all of the splats have changed. So yeah, there's some more performance measurements of that in the paper for some other stuff for modifying stuff. But let's have a look at the rendering performance. If we want to edit quickly, we also need to be able to render things quickly. So we've been taking a look at improving things like the sorting of the splats, because with the CUDA-based rasterization pipeline, we need to sort the splats first by depth value and also by tile ID, since we are using some tile-based rendering. And we end up doing a 48-bit sort with a 32-bit key of the depth value and a 16-bit for the tile ID. Now the problem here is that we're not sorting the visible splats. We're sorting the visible fragments or duplicates. So whenever a splat intersects a tile, we create a duplicate. And looking at the garden scene here, from this viewpoint, we have about 1.7 million visible splats. But because of this tile-based rendering, we end up with 4.3 million visible fragments after partitioning the splats. And this is the number that we have to sort, so it's much, much higher. So what we did for the editor here is we split the sorting into two passes, where we first sort the small amount of visible splats by the depth value. Then we create these duplicates, and with a little prefix sum, we can make sure that the duplicates or the fragments, they remain ordered by depth value. And then we do another sort by the tile ID. And yeah, basically what happens, we have this 3D.js rendering pipeline, and we just add another sort in between two stages and make the other sort much, much cheaper. So the whole thing works because the radix sort that's used here is stable. So when we duplicate the splats, we make sure that they are still ordered by depth value, and if we then sort by tile ID, all those fragments that were sorted by depth value, they remain sorted by depth value. And the whole thing pays off because sorting by depth value is more expensive. The keys are less large, and for the radix sort scales linearly with the bits in the key. So we can compute some rudimentary expansiveness value here. So with the original 3D.js pipeline, we have these 4.3 million fragments for the garden scene here. Multiply that by 48-bit, that's how large our key is, and we end up with an expansiveness about 206. And with this two-pass approach, we have 1.7 million visible splats that we sort by the depth value, so with the 32-bit key, plus the 4.3 million fragments that we sort by the tile ID. So with an expansiveness of 123, so quite a bit lower than the original one here. So looking at some performance measurements for the garden scene, that decreases just the sorting time from 0.48 milliseconds to 0.3. For the campus scene, we have much, much more visible splats in there. And here we have a performance improvement from 1.8 to just 1 millisecond, so about 50% increase. From a close-up viewpoint, if you have another viewpoint from farther away, we have, still have a performance increase of the sorting duration of about 30%. So yeah, this is one of several improvements to the rendering pipeline. Another thing we've taken a look at is imbalanced workloads. Because you have the Splat rasterization pipeline, the last step is the actual rasterization, where we blend the splats together from front to back for each of the tiles. And the problem here is that some of the tiles have much, much more splats than other ones. And we only launch one thread block per tile. So some of these thread blocks, they have much, much work to do. And the GPU has to wait until the slowest running thread block is finished. So in terms of GPU utilization, it looks like this here. So up to about halftime, we have a very good utilization. And then utilization drops because all of the cheaper tiles, they have finished rendering, and now some thread blocks are still busy with rendering the remaining tiles here. And this varies greatly from the viewpoint. In some viewpoint, it's not a problem at all. And in other viewpoints, this might add 5 milliseconds to the rendering time, where just maybe 1 or 2 out of 100 streaming multiprocessors is actually doing work. So in virtual reality, this can actually be fixed quite nicely and easily. Here we have the performance measurements and profile for virtual reality. So first we render the left eye, then we render the right eye. And in both cases, we can see that there's really poor utilization towards the end of the pipeline. So what we can, of course, do is we can use concurrent CUDA streams in order to do some rendering for the right eye, while the left eye hasn't even finished yet. And then we get utilization like this here. So we can squeeze 1 or 2 milliseconds again out of that. There's some considerations for that, and if you just simply duplicate everything, then you also have to duplicate the buffers. For example, we have to do some sorting. We need some intermediate sorting buffers, and we would have to duplicate that. Same for the staging buffers and some other buffers. So with that in mind, we didn't duplicate everything because some of the stages, they have a fairly good utilization. So sorting could probably be better, but it already has a pretty good utilization. So we do not overlap the sorting. So sorting still happens one after the other. What we do instead is, while the left eye is mostly idle but not finished yet, we already do some sorting for the right eye. So performance-wise, this gives us these improvements here. For the garden scene in virtual reality, with the single stream approach, it takes about 8 milliseconds, and with the concurrent CUDA streams, 6.5 milliseconds. Similar for the campus scene, campus has 28 million splats, and here it improves the performance from 16 milliseconds down to 13.8 milliseconds. So, yeah, another one that I'd like to mention here, so there are more in the paper, but this one is really stupidly easy and works out quite nicely. Progressive spherical harmonics. The problem with spherical harmonics is they're super expensive to evaluate, especially if you use this, so which we do from the original approach. Spherical harmonics based on floating point precision, that adds so much memory to the whole thing that this entire rendering pipeline becomes memory bandwidth bound. But the spherical harmonics, their effect is actually relatively subtle, and they do not change the color values that much under slide rotations, under slide movements. So what we can do here is we do some progressive evaluation of the spherical harmonics. So in each frame, we only evaluate the spherical harmonics for 10% of the splats, and we bake that in a color buffer. And in another frame, we take another 10% and bake that into a color buffer that we then use for rendering. And most of the time, that's barely noticeable at all. So even in VR, where you have a lot of head movements, you usually don't notice that. Performance-wise, for the garden scene, we here have performance improvement from 2.6 milliseconds down to 1.9 milliseconds. We also try to go a little further and not do 10% per frame, but only update 3% of the spherical harmonics per frame. And here we have some diminishing returns. So it doesn't improve performance much anymore, but now you can clearly notice that the evaluated color values, they lag behind a bit. So, so every 10th frame updating color values, also not just 10% of the spherical harmonics per frame. This is kind of a sweet spot that works out nicely. So, yeah, of course, there are still some limitations in future work, and one of them is right now for transformations, when you select something and transform it around, we still update all the spherical harmonics per frame, and this is really super slow. So just updating the spherical harmonics as well makes it 14 times slower. So here we also want to do progressive spherical harmonics in the future, where we only update a small amount per frame. And also what we can also do is right now we apply this to translation, rotation, and scale, update the harmonics, but in reality we only have to do that for rotation. Yeah, and for the undo and redo, we also want to take a look at transforming so at being able to do the transformation and undoing the transformation in a lossless manner. So, but without having this explosion in memory. So what we could probably do is compress original values. And one thing we could do is we still do it like now, where we apply the inverse transformation matrix and then do some delta encoding just to apply this tiny difference to get a true previous value. And then something that's more of a limitation here than something we can address is what we noticed is when you paint something in this Gaussian splat data sets, basically you're painting into sparse geometry, like doing vertex painting on a mesh model. And the problem here is that all of these reconstruction approaches, they try to fit as few Gaussians as possible. So if you have a very homogeneous surface, a wall with a single color, you might have one splat representing a large region, so of course you cannot paint fine details in there. Yeah, maybe something like textured Gaussians could do that, but right now this is more of a limitation. In any case, here one final video where we have this statue here. Let's just assume these are some Roman statues that lost their color values, and in VR we can then nicely recolorize them. And yeah, whenever you do something wrong, you can always easily undo and redo, like deliberately wrong here, just brush it and then undo and redo it. Yeah, with that, thank you for attention, and if you're interested in trying it out and the source code, you can take a look at here at the GitHub repository.
Thank you, Markus, also for making up for some of the lag we had. So we have more time for questions now.
So nice talk, thank you very much. So original approach was do this tile-based stuff, but now everybody seems to be switching to graphics-based splats. So you just cover in a splat with a couple triangles and do 2D. So you considering switching from compute based to rasterization based?
Not really, because I'm not smart enough for Vulkan, so I'm still using CUDA for any kind of rendering, and their tile-based still seems to pay off for everything.
More questions? Well, not. I don't see one, so I actually have one. Obviously, if you're like cloning parts of the scene or moving it around, the fact that the lighting is baked into the Gaussians becomes a problem of inconsistency at some point. Do you have any ideas on that issue?
Not much. So the idea here was more to have something like a Photoshop for Gaussian splats. And in Photoshop, we also don't really have real illumination models usually. So for example, a fun thing, if you insert something into the scene like the truck before, of course the shadows won't match. So we were more trying to have a painting tool to paint the shadows into there to match that. But regarding illumination, we haven't really done anything here.
Okay. We have one more.
Hi, great talk. For your unbalanced workload issue, have you considered just kind of like sorting the tiles? So, you know, the tile, you evaluate the tiles that have the, you know, like the largest amount of splats in them.
Because to the more expensive tiles first, right?
Exactly, and then fill in the gaps at the end.
We have tried that, but it doesn't bring that much because they might still take 5 times or 10 times longer than all the other ones. So even if you start first, it doesn't improve much. Another thing we tried is that we use multiple threads per tile. So instead of just one, have 10, do one single tile.
Yep.
And this works. Does improve some stuff. There's also a secret paper from Bernard Kerbel this year who's doing this. So they kind of did this before us now. We tried it for Splatshop. And it did work, but we didn't do it because for inserting some stuff into the scene, we currently rely on having a depth buffer so that we know where to drop things off. And if we do that, if we would use 5 thread blocks per tile, then we have some difficulties finding out where the depth value should be.
Right. Okay, thank you.
Great. So if there are no more questions, then let's thank Markus again.